Hi, my name is Julius. I will be presenting today bounding expert hierarchies, which is the result of my time last year at UCL, University College London, and joint work with Tobias Ritschel. In this project, essentially, we are trying to apply the mixture of expert architecture for neural networks, which is quite popular in large language modeling, to the problem of bounding. So just to give like a brief recap, I assume probably most of you are familiar with this, but what is bounding? Well, we have a query, for example, array. We have a scene consisting out of geometry and triangles, and we want to find out if the array is actually intersecting with our scene. Of course, we can simply evaluate this. This is like very trivial, but this can take a lot of time depending on how complex our scene is. And even all the arrays that don't intersect in the end with it, we would still have to evaluate. So this is kind of slow. So most of the time, people will build a proxy that is much easier to compute and faster, especially, and is bounding our scene, such that we can use this as an early termination point in order to avoid the compute-heavy scene evaluation. Well, there are famous data structures for building such a proxy. One of those is a bounding volume hierarchy. This recursively splits space into subregions using geometric primitives, and this is extremely fast and used quite a lot in ray tracing. But the downside for this data structure is obviously you can have quite deep hierarchies, but they are still limited to geometric primitives, so the kind of shapes that you can represent are obviously constrained to the primitives itself, so they are not bounding necessarily extremely tight. Prior work has looked into this problem, and they wanted to fit more tight, and the way they approached it is they simply replaced the BVH with a multi-layer perceptron, which then is bounding the entire scene. And of course, as we all know, a neural network is not constrained and can model any arbitrary shapes, so we can fit much tighter with this. But a neural network doesn't scale that well, because if we want to have a more complex bounding, we essentially need to have more parameters, which makes the inference quite slow. And our approach now tries to kind of marry these approaches and take the best of both worlds, where we locally bound with many small neural networks, such that when we evaluate a query, we only need the local one that is needed. So we can be tight and fast, essentially. The architecture, as I said at the beginning, that we are using here is a mixture of experts, and this is essentially a weighted combination of two types of neural networks, where we forward pass our query in this case, and we get out a scalar that is indicating, for example, the occupancy. So first of all, we pass our query to a gate neural network in this case, which is producing a probability distribution with m dimensions. And respectively, we have then also m small neural networks that are learning or bounding locally. And these experts can be understood as sign distance functions, essentially, that are all local. And the sign distance function, as we all know, they map a query to a scalar. And the most obvious thing to do, essentially, is to combine the distribution with the scalars from our experts and compute this into a single output of our MOE. And the distribution here would kind of act as how much should each expert actually be involved in answering our query. But if you listen carefully now, you must realize that actually on the previous slide we claimed that our speed comes from the fact that we only need one of those experts and not the entire neural network or like all of them together, because otherwise we could also just fit it with a single MLP. And this brings us to certain objectives that we have to enforce during training, such that our MOE behaves in a way that is actually suitable for being faster. And we will go through these auxiliary losses now one by one. So first and foremost, I guess it's the most trivial to understand. Of course, we want our gate to kind of indicate only that we need one expert and not many. So in this case, the distribution for our query that the gate produces should be one hot. So the gate is really certain that I only need, in this case, the orange expert in order to answer our query. And this means the gate has to be certain, and more formally speaking, the uncertainty in this distribution should be 0. And the great thing is we can actually measure this using the entropy. So during training, we minimize the entropy for these distributions that are being produced by our gate. Well, with this at hand, our distributions individually would be sparse, but we could be in a scenario where now the gate is actually saying, okay, now we just use one expert and basically map all our queries to the orange one in this case. That's not what we want. Essentially, we want them to be uniformly distributed across space because each expert has, by design, the same number of parameters, which translates to constant inference time independently of which expert we are using, and therefore they have the same modeling capacity. And how do we measure this? Well, we can compute the mean distribution that is produced by our gate and basically enforce this to be uniform. And this distance, if it's uniform or not, we can compute the distribution distance using KL divergence and also enforce this during training. Quick note here, we are actually doing this only for the occupied, or on this example for point samples only that are occupied. This means that we can tailor the gating and the uniform distribution only over the scene where the geometry actually sits and avoid experts that are assigned to an empty region where actually nothing is to bound. And then last but not least, of course, we are building and modeling a proxy. So we need to make sure that we are covering the entire scene. This is just reusing essentially the introduced loss from prior work, which is an asymmetric binary cross entropy. For those of you who are not familiar with binary cross entropy, this is essentially a loss function for dealing with a binary classification. So we have two types of labels here, positives and negatives, and the asymmetry arises if we don't weigh them equally during computing the loss. So essentially throughout training, what they proposed is shifting the focus in this loss more towards the positive samples, such that by the end of the training, the model is more and more allowed to loosen its bounding in order to actually cover the entire scene. And with all of this at hand, we can train a model like this. We have the experts here colored, and we might realize that as we increase the asymmetry, somehow the experts are blowing off their boundary and we lose all of the tightness. At first glance, this seems like something we can actually fix by adjusting the hyperparameters when we enforce conservativeness, because the strict false negative rate of 0 might interfere with the signal. So we adjust the learning rate accordingly if we increase asymmetry, for example. But we can still see some cases where the experts are not receiving a proper learning signal. And that's why we kind of adopt a focal loss, which goes back to a paper 10 years ago, which had kind of a similar issue, which essentially rescales the binary cross entropy in the way that more aggressively penalizes still wrong classified labels, like very heavily wrong classified labels, in order to shift the learning signal. This might sound more confusing than it is, but I can assure you this is literally just like basically rescaling the loss. And with all of this at hand, essentially we have now a model that is like behaving as we want and still fitting tight, even if we enforce conservativeness. And we evaluate our method against two baselines. In this case, the bespoke single neural network approach with the MLP, and then also the MOE with a grid gating instead of a neural network as the gating mechanism. And this becomes evident if we look at the coloring here in 2D, where we can see essentially the grid appearing. Same applies to 3D, where we can also see the 3D grid appearing in the MOEG. And in 4D, for example, this is an example from the very beginning where we used the neural network. Here, it becomes even more obvious that what the power of the neural network gating, so essentially the neural network models the space partitioning. The space partitionings can be disjoint, which is not possible in the BVH, and they can also live throughout space and time in order to achieve this bounding tightness. So we bundle our results into these tables where we have two types of spatial queries and the bespoke dimensions, and we test and essentially create a graph for each of the evaluated methods at 3 different model sizes. So first we have roughly 500 parameters in total in each model, and then this goes up to 20,000 parameters in total. And then we evaluate those sizes against all of the different scenes that you can see beneath. And essentially what we want to show here is how, like these are plots that are showing query time relative to bounding tightness. So a very fast and tight method will be in the lower left corner and constitutes the optimum. And our graphs should show how the scaling behavior is. And the most ideal scaling would be we can increase the number of parameters and the query time never goes up. So it would be a vertical line. So the steeper the slope, the better. And essentially what we can see, and that's already what we were claiming at the beginning with the MOE approaches, we are much faster than the MLP, roughly four times in the best cases. And this is due to the fact that we simply have less active parameters during an inference call. But on the other hand, there still arises this question of like, okay, but grid gating, neural network gating, what is actually better here in this case? Because it looks as if there is a trade-off. And in order to understand if this is actually true, we have to understand again how this grid and expert assignment works. Really basic, but the most minimal grid we can create in 2D are 2 divisions per dimension. So we get 4 grid cells and 4 expert networks at the minimum. Then in 3D we get 8, in 4D we get 16. And then we enter like a higher dimensional space, like for example this robot state space, which consists out of 6 joints and obviously the 3D space. So we have a 9-dimensional space. And the minimum number of grid cells that we get here is 512. And this becomes an issue if we actually have now, let's say 100,000 parameters that we want, 100,000 parameters that we want to distribute. Because if we have that many experts, this means that we actually have many experts, but many small experts. So their capacity to model boundings is limited. And if we run this, and these are the examples of the 3 baselines that we test, where each model has in total 100,000 parameters, but obviously the MOEG with the grid is constrained that it has 500 experts, and the neural network could fit any arbitrary number. So the main difference here is why is the grid gating so much less tight, whether it's because it has many experts, but less powerful experts, and the neural network gating has fewer experts, but more powerful experts, and can therefore model more tight this space. So the neural network is overall just more flexible in basically modeling space partitions. And also these high dimensional spaces are often sparse anyway. So if we have a uniform grid through space, then we assign also some experts to an empty region where literally nothing is to bound. When it comes to speed, I guess this is quite similar still to previous results. Of course, the grid is no neural network, so the inference time is much, or not much, but it's like that's where the inference boost comes from when we compare the grid gating versus the neural network gating, and why the MOEG is always faster. So this is like one of the main differences between this method, and also still a limitation of the MOE with the neural network, because essentially if we have more experts, this means we need to have more parameters in our gate, because our gate distribution has more dimensions, and therefore this grows, even if we choose always the top 1 expert only to execute. Then, of course, the BVH is still like much faster when it comes to queries. So when we compare with NVIDIA Optics, for example, the BVH is still like 60 times faster. Then conservativeness, as I talked about before, this is only an approximation, of course, because we are dealing with a neural network which we train with samples. So, of course, this cannot hold for like the entire continuous space, but only for the samples that we use. Even if we would use like all available floating point numbers, this would still only be an approximation of conservativeness. And this has also been claimed by all of the previous methods that have used this technique. But yeah, it's holding in that sense at least. And then deeper hierarchies. In our case, the neural network for the gating is a root to leaf mapping in a direct fashion. And there's no way of like terminating in between these layers. Whereas in the BVH, the speed also comes from the fact that we are traversing the tree, and the moment we go into a nested primitive, we can basically terminate and stop continuing going down the tree any time, which is not the case in the gate at the moment. So I guess to wrap this up with our approach, essentially we try to combine bounding tight and inferring faster than the BVH, at least to some extent, and also the MLP approach. Our project page is here, and I'm happy to take questions.
Thanks for the presentation. I think the work is very interesting. I was wondering about this number of experts and why you want the experts to be uniform. So you cannot have like a junior, middle, a senior, a manager. I don't know. Why uniform?
Yeah, that's a fair question. Well, the main reason why we have them kind of uniformly distributed is for the fact that we want to have a constant inference time. If we make, for example, one the manager in this case and someone like more junior, then this would mean in this architecture that they have different number of parameters, right? And they can actually then cause different amounts of time when inferring. And we want, because we don't know at the beginning which expert we are picking, and this could lead to the fact that some queries may be super fast to compute and others may take a lot of time. And that's why we give every expert the same number of parameters, and this translates to a uniform distribution across the scene because we assume kind of a uniform complexity across the scene. Of course, you could try to incentivize this in a non-uniform way, for example, using curvature, and then you try to center experts more around like curvature space, and then it's like not spatially uniform, but at least that's the reason why we did it in a uniform fashion.
And what about the number? So the number of experts?
The number of experts.
Depend on the scene complexity or something?
Well, here we just mentioned it on the left, right? So we have the number of experts, obviously you can change, and we show this in these plots also, because it's not indicated here, but if you go in the paper, you will see this. Of course, you can simply increase the number of experts. There's nothing speaking against this, if this is your question.
But do you have the experiment which is the minimum number of experts that give you the accuracy that you want or something like that?
No, we didn't try this, but you can only fit 2 if you want. Mm-hmm. This is like, if you have more parameters, then obviously you can fit more complexity, right? This is like giving more variables to your function, essentially. Mm-hmm. And if you have like more experts or more powerful experts, this is a bit like a design question, I guess.
Okay. Thank you.
You're welcome.
Other questions?
Have you tried using more like a hierarchy of experts to find other experts? It seems like a natural extension, and you would be able to make the MLPs much smaller.
Like basically nesting these kind of structures in each other. Well, we haven't tried this. Of course, as you said, it's kind of like the most obvious thing to do next. But we haven't tried.
Other questions? So I actually have one.
Yeah, sure.
So if you up-level this a little bit, and you have this performance delta with BVHs, for instance, why do you think you would want to use a mixture of experts rather than a traditional approach?
Yeah, no, fair enough. I think one of the big advantages, of course, that we have with this, that essentially the question boils down to, okay, what's the difference between the space partitioning of a BVH versus this neural network? And because we're using a neural network, we can essentially model like a higher dimensional space partitioning, which, as I mentioned during the talk, you can have out of a sudden disjoint partitions, which then are still activating the same expert. In the BVH, you have a box, and in these boxes you have more boxes, and then so on. But here you can have, a box here and a box here, and in high dimensions they're actually one. And I guess this gives you, in some cases, more freedom to discover actually space partitionings that are like highly non-trivial. Of course, this is like more of a hypothesis, I guess, but this is the advantage that we see.
Any other questions? Oh, there's one here.
Thank you. Is there a point where, like, if you have a tree and like it's very difficult to do a proper, like, very good PVH for a tree, and when you do ray tracing, you will have like many divergence because like one pixel you will traverse everything because you miss everything, but the other you will stop. Is there like a point where using a very tight neural bonding volume like Q, that basically you get back performance?
Could you elaborate? Sorry, I didn't fully get it.
Yeah, so it's more about like if you ray trace like a dense tree and like you will have like some part that you will traverse all the BVH because you miss all the leaf and stuff like that, but the neighbor, like, it's not the case. So there's a AV cost for that. Like, is your method at some point getting better result than like ray tracing through a bad BVH will get you?
Well, I hope I get the question completely right. Well, as I said earlier, because we use the gate for the space partitioning, there's like no like termination in between, so we have to execute every time.
Oh, okay.
And if you are using a BVH, right, then you are traversing the tree structure, and if you have that ray, like the moment it's not intersecting, you can skip this, and you don't actually have to go down to where the triangle is sit.
Yeah, but for a tree, it's like it doesn't happen often. That
because you have so many.
Yeah.
I guess you would still have to traverse, and I guess the only difference is probably because the tree is so dense, right? You have a lot more like primitives that you need to use, and therefore the reason that actually the ray is intersecting with more primitives, whereas this technique is modeling an SDF, right? So we can like be much tighter. So I guess my answer to this question would be probably you could avoid having this ray collision in trees because you can fit so tight. Yeah.
Okay.
All right, I think we should, well, one more.
Yes, thanks for the presentation. I was wondering, how do you ensure continuity between the intersection output, that is basically either the distance to the intersection or the bicentric coordinates between partitions?
The distance between, sorry, I did.
So when you do the intersection, you need to know, for example, the distance to the surface you intersected, right? Mm-hmm. And if you have disjoint section and there's an MLP that predicts, for example, the distance, I don't know if it's what you do, but you have to predict something, and this something you predict between MLP might be not continuous when you transition between one partition to the other, right? So I'm wondering how you do that.
Well, we don't use the distance. We simply, like we only, in this case, we only determine the output, like if it's actually intersecting or not. There's like no distance actually measured then involved, if this answers
okay,
the
but
question.
So you cannot know what's the position of intersection afterwards?
No, so it's essentially like we have a ray or like a point query, and all we get out of like what the output is of the model is it intersecting, is it occupied? And that's it. Like we don't get the actual intersection point.
Okay, so that's something you have to compute afterwards.
Yeah.
Okay.
Theory.
Thanks.
All right, let's take any further questions offline, and let's thank our speaker and all of our speakers again.